For most people, reaching for an object is automatic. You see it, you move your hand towards it, and you grab it. For someone who cannot rely on sight, that simple action becomes very difficult. Hello, respected judges and fellow inventors. This is what inspired our project. What if a system can find an object and guide the user hands towards it? This is what Guide My Hand is designed to do. Our system combines vision, depth sensing, speech recognition, and touch to provide real-time guidance towards everyday objects. In simple words, we are not only helping the system detect objects, we're also helping the user reach them. The motivation behind this project is independence. For visually impaired individuals, finding objects like phone, bottle, or keys can be difficult. This may require searching by touch, relying on memory, or asking others for help. Many current assistive tools can detect objects or describe the environment, but they do not guide the user's hand accurately towards the object. This gap is what our project focuses on. Guide My Hand responds to a voice command, detects the target object, estimates its positioning, and guides the hand in real time using vibrotactile feedback. The problem is clear. More than 2.2 billion people live with some form of visual impairment. For many of them, locating everyday objects is still a daily challenge. This leads to frustration and slows down our daily lives. Although many tools support navigation or awareness, they do not provide direct real-time hand guidance towards a targeted object. Our project addresses this missing step, helping the user reach the object. So, for our literature review, we found that many existing systems solve only part of the problem. Some focus on object detection, some focus on speech, and others on audio or tactile feedback. Our approach is different because it combines vision, depth, speech recognition, and vibrotactile feedback into one system. This allows Guide My Hand to provide practical hand guidance for reaching and grasping, not only object awareness.
Now we'll move to the proposed system and explain how Guide My Hands work, from the overall design to the dataset and prototype. This diagram presents the overall architecture of Guide My Hand, which functions through 4 critical stages. Each stage is designed to provide a real-time, intuitive guidance enabling visually impaired user to locate objects independently. The system initially operates in a standby mode to reduce power consumption and processing load. When assistance is required, the user activates the system using a voice command such as Guide My Hand. Once the keyword is detected, the system transitions from standby to active mode and initiates the guidance pipeline. After activation, the system waits for a target object command, for example, find my bottle. This command is processed using the Whisper Automatic Speech Recognition model, which converts speech into text through improving audio clarity, extracting relevant speech features, and accurately transcripting the command. The recognized command is then passed into the main processor. Here, the Raspberry Pi 5 integrated with AI Hat, which coordinates the AI model's camera input, depth data, and feedback output. The AI Hat accelerates model interference, reducing latency, and enabling real-time processing. Once the command is interpreted, the system enters the object detection stage, powered by a fine-tuned YOLO V8 model. Using the RealSense depth camera input, the model detects and localizes the target object in real time by generating a bounding box around it. This provides precise position information, forming the basis for accurate tracking and subsequent spatial guidance. After detecting the object, the system transitions from the visual recognition to spatial understanding. YOLO V8 provides the object 2D position, XY, through the bounding box center. The depth camera provides the distance, which is Z value, at the exact point. By combining these values, the system generates a 3D estimation of the object's position. In the final stage, the system converts spatial data into real-time physical guidance. The calculated X, Y, and Z coordinates are mapped into directional vibration cues, delivered through a vibration band. Vibrations indicate directions such as left, right, up, down, forward, and backward. The feedback is continuously updated, and the user moves to create a dynamic interaction where the system actively guides the user hand step by step until the object is reached. Finally, the user can deactivate the guidance at any time using a voice command such as stop guiding. This gives the user full control over when the system starts and stops, while also helping to reduce unnecessary power consumption.
To make sure our system performs well in realistic conditions, we built a comprehensive dataset using both online sources such as RoboFlow and real-world images. The dataset focuses on common everyday objects, including cups, bottles, laptops, remotes, and cell phones. To improve model robustness, we included variation in object style, camera angle, background, lighting, and scene conditions, so the model would not depend on one fixed environment. After collecting and annotating the data, we split it into training, validation, and testing sets, then applied augmentation before training and fine-tuning the YOLO V8 model. This process helped us prepare a more reliable detection model for real-time object guidance. This prototype combines advanced hardware and software to create a fully functional real-time object guidance system. It brings together the main processing unit, camera input, microphone, power supply, vibration driver board, and haptic feedback band into one compact wearable design, as you can see here. The haptic band includes 6 embedded vibration motors, allowing the system to deliver directional cues across multiple movement directions. What makes the prototype practical is that it is designed for real usability. It is wearable, adjustable, and support guidance without relying on constant audio instructions.
Now we will move on to the results and analysis. In order to evaluate Guide My Hand, so we tested the system at different levels. First, we tested object detection using static images from the dataset. Then we tested real-time detection with a real-time camera in order to check the accuracy, stability, and response time. We also evaluated depth-based interaction in order to confirm that the system can estimate distance and also provide directional guidance. Finally, we tested the speech recognition model using 200 English speech samples with clean and complex accents. Performance was measured using precision, recall, MAP, confusion metrics, and F1 score. The object detection results demonstrate that the model performed with high accuracy across the selected object classes. So the model achieved an F1 score of 0.97, which shows a strong balance between precision and recall. The precision recall curve reached an MAP of 0.989 for all classes, which indicates that the model was able to detect the target objects consistently and accurately. The precision confidence result was also reached around 0.972, which shows that the model maintained reliable prediction at high confidence level. This is important because in our system, detection accuracy directly affects the quality of hand guidance. Overall, these results show that the detection model provides a strong and dependable foundation for the real-time guidance process. This result shows that the model learned during training. So the training on validation losses decreased over time, which indicates that the model was improving and learning the object features effectively. At the same time, the precision, recall, and MAP curves increased and remained stable, showing that the model was not only learning but also generalizing well during validation. So this is important because a stable model gives more reliable detection in real time.
So for speech recognition, we evaluated the Whisper Distill Large V3 model using 200 English speech samples. The results show stable recognition performance across both clean and complex accents, with a word error rate of 6.78% and a character error rate of 1.56% in both tests, as we can see here in the table. The main difference was processing time, where complex accents required slightly longer time, increasing from 12.15 to around 14.10 seconds. This shows that the model maintained accuracy across different accents, while speed optimization, on the other hand, remains an area for future improvement. So these slides demonstrate the real-time centering and guidance mechanism. We tested all main use cases, including when the object is on the right, left, above, below, far from the user, and when it becomes centered at the correct distance. Across these cases, the system was able to detect the object position accurately and generate the correct guidance action. The center of the frame is used as the reference point. If the object is not aligned with the center, the system determines the required movement direction. Each direction is then mapped to a specific vibration motor, allowing the user to receive immediate haptic feedback through the band. Once the object is centered and at the optimal distance, the system stops the guidance, meaning the user has reached the target object position. These results show that Guide My Hand can translate detection and depth information into accurate real-time hand guidance. So in conclusion, Guide My Hand successfully demonstrates a vision-based assistive system that helps visually impaired users locate and reach everyday objects more independently. The system combines speech input, object detection, depth sensing, and vibrotactile feedback into one wearable solution. Our results showed accurate object detection and effective real-time guidance, proving that the system can translate user intention into physical hand movement. So for the future work, we aim to improve performance in more cluttered real-world environments, expand the number of detectable objects, and further refine the wearable feedback system. Overall, Guide My Hand moves assistive technology beyond object awareness and toward real interaction, helping users not only know what is around them, but reach it with more confidence and independence. So thank you for your time and attention.